Hi, I'm Teixeira. For millions of people, the last mile of broadband internet ends miles from their residence, leaving them without broadband connectivity. In the United States, due to poor quality broadband coverage maps, millions are the margins of error in estimates on how many Americans are without broadband access. Today, I'll discuss our effort to build a more accurate broadband coverage map by querying ISPs for millions of addresses, and to conduct the largest scale evaluation to date of where, why, and to what extent the US overstates broadband availability, performance, and competition. This project was led by David Major while an undergraduate and mentored by myself and my advisor, Jonathan Mayer.
In 2020, billions of people have come face to face, virtually, with the pitfalls of conducting our daily lives through broadband internet. The forgotten families and communities that lack broadband coverage suffer the most. Bridging this digital divide is an urgent public policy matter and requires governments to build accurate broadband coverage maps on who has or who can get broadband coverage. In the United States, the Federal Communications Commission is responsible for collecting broadband coverage data and encouraging deployment. However, its coverage maps have been widely criticized as too inaccurate to be useful for connecting Americans that lack broadband, and estimates of FCC errors have revealed troubling overstatements of coverage. Worse, the FCC is set to auction off billions of dollars of funds for rural broadband connectivity this month, and poor coverage maps hurt the FCC's ability to direct funds appropriately for new infrastructure. I'll start by explaining exactly why the FCC's broadband maps have been so criticized, and describe related efforts to evaluate the accuracy of the FCC's maps and to develop more accurate coverage maps. I'll then describe our rigorous method for building a coverage map using millions of queries to ISPs. Finally, I'll use our map to demonstrate how the FCC coverage maps consistently overstate broadband ability, performance, and competition, and to provide new estimates on the number of Americans without access to broadband internet. The FCC collects broadband coverage data from ISPs through a process called Form 477, in which ISPs are required to submit biannual reports on where they provide fixed broadband service, such as fiber, cable, and DSL, at speeds greater than 200 kilobits per second. The result is a public dataset of broadband availability and a yearly broadband deployment report. Last year, the FCC estimated that 21.3 million, or 6.5% of Americans, did not have access to benchmark broadband, which the FCC currently defines as 25 megabits down and 3 megabits up. Good intentions, but in practice, the maps are very prone to overstate coverage for three big reasons. First, the FCC collects data at the granularity of census blocks, geographical regions whose borders are drawn by roads, rivers, property lines, and other physical or legal land features. The size and population of census blocks can vary greatly, from hundreds of residences in densely populated urban areas to hundreds of square miles in rural areas. Second, the FCC allows an ISP to claim it covers or provides service to a census block if it covers just a single residence in that block. Moreover, even if an ISP does not provide coverage to a single residence in a census block currently, as long as an ISP could soon provide coverage to a residence, where the FCC is vague on the meaning of this, the ISP can still claim coverage. Intuitively, such loose reporting thresholds may easily overstate the true prevalence of broadband connectivity, or lack thereof, and allowing ISPs to report potential coverage is antithetical to the goal of understanding where Americans do not have broadband today. There have been three notable efforts to examine FCC coverage overstatements, all reported last year. Microsoft studied the related question of how many Americans are not using benchmark broadband by observing Windows Update download speeds, and found the answer was over 48%, or around 162 million Americans. Broadband Now, a company that aggregates broadband coverage data and advocates for broadband expansion, conducted a study using a similar methodology to our own. It tested the coverage for 9 ISPs using over 11,000 addresses, and found that 41 million, or 13% of Americans, did not have broadband access at all. This is double the FCC's estimate. The Broadband Now report is a valuable contribution, but it comes with significant flaws. First, it is not clear whether Broadband Now tested benchmark broadband overstatements, as the FCC reports, or overstatements of any fixed broadband. If the latter, the Broadband Now report may inflate estimates of FCC overstatements, as our study finds greater overstatements at lower coverage speeds, which are not comparable to the FCC report's benchmark estimate. In addition, Our study uses a comprehensive and rigorously filtered dataset of residential addresses, orders of magnitude larger than Broadband Now's study. And we develop and evaluate a precise mapping from ISP responses to coverage outcomes. Also, CostQuest, a telecom consulting firm, aggregated public and proprietary datasets, including property tax records, ISP address lists, satellite imagery, and crowd worker labeling, to measure coverage in Missouri and Virginia. It found that 16% of structures in Missouri and 19% in Virginia did not have broadband access. Given the poor quality of its Form 477 data, the FCC itself, as well as other organizations, are attempting to build more accurate broadband coverage maps. The FCC proposed last year to have ISPs submit polygonal shapefiles to indicate coverage regions. However, there is currently no restriction on the accuracy of shapefiles beyond technology-specific buffer zones that could be miles long. Meanwhile, other government agencies, such as the NTIA and the California Public Utilities Commission, are attempting to build coverage maps by aggregating data from ISPs and communities. Our study focuses on coverage data that we collect from ISP broadband availability tools, or BATs. These are public web pages that consumers can use to check coverage for their address. ISPs have significant incentive to offer accurate coverage data to consumers through their BATs. A false negative means a lost customer, while a false positive means the ISP wastes resources engaging with the customer, potentially even sending out a service technician to inspect coverage. Now, I'll describe our rigorous methodology for building a dataset of broadband coverage. I'll start by explaining how we select ISPs to study and assemble a dataset of over 19 million addresses the ISPs claim to cover. I'll then detail how we reverse engineer each ISP's BAT through manual analysis and build a Python client to query BATs at scale. Finally, I'll discuss how we iteratively create and evaluate a taxonomy that maps BAT responses to coverage outcomes. The result is over 35 million coverage responses to compare against FCC reports. We use Form 477 data as a starting point to identify 9 major ISPs with large geographic and population footprints, and which have public BATs which we can query. We term these major ISPs, and together they cover over 90% of the population in the states we study. I'll explain how we select states on the next slide. Each state also contains a number of smaller ISPs, which cover a relatively small portion of the total population, and which generally do not have public BATs. We term these local ISPs, along with major ISPs where they serve a small portion of the state population. For analysis, we assume that Form 477 data is 100% accurate for local ISP coverage. There are few public data sets of US residential addresses, as most are crowdsourced and of unknown quality, privately owned, or otherwise restricted. We rely on the US Department of Transportation's National Address Database, an ongoing initiative to create a comprehensive public data set of addresses by collecting data from local and state partners. We select 9 states which the DOT has accepted into the NAD, though the data collected is not necessarily complete nor perfectly accurate. Since our study targets residential addresses, we filter the dataset to exclude non-residential address types, which the NAD provides for some addresses, and we also exclude any addresses with incomplete data. To further increase confidence that our dataset contains only residential addresses, we filter the dataset using 2 US Postal Service datasets, which we access through a commercial partner. We confirm that each address is able to receive mail using USPS delivery point validation, and that each address is subject to residential mail rates by checking the residential delivery indicator. The result is a set of over 19 million residential addresses to query. Next, we reverse engineer the 9 ISP BATs and build a Python client to support automated BAT queries. We start by manually querying each BAT in the browser with addresses that produce 3 coverage outcomes: covered, not covered, and address unrecognized, while logging web traffic. We observe that each BAT requires distinct logic for formatting query addresses, submitting requests, and parsing responses into unique response types. For example, some BATs are implemented as RESTful APIs that respond with JSON data, while others are ordinary web pages with DOM elements we must parse. Some BATs require multiple web queries per address or session cookies to receive a response. Here, we show an example JSON response from Verizon. We create an initial taxonomy for each BAT by identifying the relevant response fields that indicate the response type, underlined here, and map them to the relevant coverage outcome. This address is recognized and has Fios coverage, but not high-speed internet, or DSL. We then build this logic, including querying, parsing, and labeling responses in our taxonomy, into a Python client. With our automated client, we then query the major ISPs that cover each address, resulting in over 35 million queries. Our data collection took place from January to August 2020, and we iteratively parse new response types as we observe them, described next. We also rate limit our client to ensure that it does not interfere with other users accessing the BATs. Whenever the client encounters a new response type, we query that address manually to understand how the response type should map to a coverage outcome in our taxonomy, presuming that the outcome presented visually to users is the correct outcome. The proper coverage outcome is often unclear, however. Consider these two responses from CenturyLink. Both appear to say that the address is not recognized. When ambiguities arise, we manually attempt to discern the proper outcome, including by making more queries. In this case, we find that the bottom response also appears for non-existent addresses, while the top does not. So we label the bottom as unrecognized and the top as not covered. We end up with a mapping from every BAT response type to one of 5 coverage outcomes: covered, not covered, address unrecognized, business, and response unknown, where the response is ambiguous, such as asking to call for more info, or in one case where we are unable to parse the response type. We treat business outcomes as unknown responses throughout our analysis. So far, we assumed that our taxonomy of BAT responses matches real-world outcomes. Now, we evaluate the accuracy of our taxonomy to test that assumption in 2 ways. First, we verify whether unrecognized addresses are actually non-existent or a BAT error by checking 40 unrecognized addresses per ISP against realtor websites, property records, satellite imagery, and Google Street View. We find that over 65% are likely residences, but conservatively exclude them from our analysis. In our appendix, and later in the talk, we present a sensitivity analysis where we relax this restriction. Second, we check the validity of covered and non-covered outcomes against telephone calls with ISP representatives. For 83 addresses across all ISPs, we find that 89% of BAT responses are accurate, which provides good confidence in our taxonomy. In the remaining cases, a representative often mentioned that a technician would need to visit the property to confirm service, while others exhibited odd behavior, such as an unpaid balance, triggering a non-covered BAT response. Now, I'll present our results. Our key takeaway is that FCC overstatements of availability, performance, and competition of broadband are widespread across every ISP and state we study. We find strong evidence that Form 477's loose reporting thresholds are responsible for overstatements, resulting in census blocks like the 8 in Wisconsin seen here, where only a small fraction of residences are reported covered by BATs. We also find potential over-reporting, census blocks where all BAT responses indicate non-coverage. And we observe that overstatements particularly affect rural and minority communities, the same communities that are often the most lacking in broadband connectivity. We first examine overstatements by ISP. In the analyses that follow, we conservatively exclude census blocks where all responses are address unrecognized or unknown. Here, we plot a CDF of coverage overstatement ratios for broadband from each ISP across all census blocks that each ISP covers, according to Form 477. The coverage overstatement ratio of a census block for each ISP is defined as the ratio of that ISP's BAT coverage to FCC claimed coverage. We conservatively define FCC coverage as all residential addresses which receive only covered or non-covered BAT responses, thus excluding unrecognized addresses and unknown responses. BAT coverage contains addresses with covered BAT responses only. We find that the median census block has 100% coverage for all ISPs, while at the 25th percentile, only AT&T and Verizon show overstatements. Overall, the trend shows that the majority of overstatements are reflected in a small number of census blocks. We now aggregate our per ISP coverage outcomes to produce an overstatement ratio for all queries, where a query is defined as a pair of ISP and residents. We use the same definition of BAT and FCC coverage counts as before, except now both counts include all queries across all ISPs. We find that 7.7% of ISP residence pairs indicate an overstatement, with 20% across rural blocks. While every ISP shows more overstated coverage in rural blocks, AT&T and Verizon show particular overstatements in rural blocks. We suspect that older broadband technology may relate to greater overstatements. In blocks where Verizon and AT&T offer no coverage over 25 megabits per second, they offer older ADSL almost exclusively, while they offer newer VDSL and fiber in blocks with higher maximum speeds. To test this theory, we threshold to census blocks where the max speed offered is greater than 25 megabits per second. We indeed observe that overstatements for all ISPs shrink, particularly for AT&T and Verizon, though a disparity in rural blocks is still present. In our paper, we additionally show the population of census blocks that experience overstatements. I'll discuss this later in the talk.
For every ISP, we observe instances of potential over-reporting, where we find no BAT coverage in a census block that the FCC claims an ISP covers. We conservatively exclude any census blocks with fewer than 20 addresses, and in which even a single BAT response from each ISP is address unrecognized or unknown. We find significant potential over-reporting for AT&T and Verizon at low speeds, which drops when thresholding to census blocks where they offer benchmark coverage. Note that we cannot guarantee that these are instances of over-reporting, as the FCC allows claiming potential coverage. Overall, they represent a small amount of each ISP's total coverage. 4BATs return convenient speed data, which we parse and analyze. For these ISPs, we plot the distribution of maximum speeds in census blocks offered by an ISP according to the FCC, and the maximum speeds according to BATs. We find overstated coverage for each ISP, and all but CenturyLink have increased disparity in rural communities. These results show that all people, even those who already have broadband access, should be concerned about FCC speed overstatements. So far, we've looked at overstatements with respect to a given ISP, but consumers may have multiple ISPs to choose from. Here, we demonstrate overstated access to broadband from any ISP. We focus on a new population overstatement ratio that measures the population of census blocks with overstated coverage to any ISP. Intuitively, we compute the population overstatement ratio for a census block as the block's population adjusted by the block's overstatement ratio. The total overstatement ratio is the adjusted population across all census blocks over their total population. In what follows, we perform a sensitivity analysis by presenting 4 methods of computing overstatement ratios and observing how relaxing conservative assumptions can change the magnitude of overstatements we find. In our most conservative method, we exclude census blocks where all BAT responses are address unrecognized or unknown. We count BAT coverage if at least one BAT covers an address, or if a local ISP offers coverage. For FCC coverage, we count addresses for which all responses are covered or not covered. Intuitively, this method does not make assumptions about an address's coverage if there is no local ISP, and if BATs return a mix of unrecognized address, unknown response, or no coverage. We also perform 3 variants of computing overstatement ratios. In the first, we allow unrecognized addresses to be included in FCC coverage counts, as long as at least one BAT reports non-coverage. In the second, we remove census block filtering entirely, and we include all addresses in FCC coverage counts regardless of coverage outcome, except in the case where we cannot parse the outcome. In the third, we remove our assumption that local ISPs provide coverage. Our primary finding, given our conservative assumptions, is that the FCC overstates access to benchmark broadband from any ISP for 0.83% of our study population. This estimate is considerably smaller than related work, especially Broadband Now's estimate of 6.5%. However, if we naively extrapolate this to the total US population with broadband coverage, according to the FCC, it would suggest that the FCC overstates broadband access for 2.5 million people, a significant number. In addition, if we do not filter unrecognized addresses and unknown responses from FCC coverage counts, we estimate that 4.81% of our study population does not have access, which would extrapolate to suggest that over 14 million people have overstated coverage. We also find that the FCC overstates competition, or the number of ISPs that residents can choose from. A healthy broadband market should provide customers with multiple options for ISPs, as competition can lower prices and improve reliability. Here, we plot the distribution of competition overstatement ratios for census blocks in each state. The competition overstatement ratio of a census block is defined as the average number of bats that provide coverage to each address in the block. We find significant overstatements in rural areas. For example, in Virginia, the SCC may double the number of providers for 1 in 4 census blocks. Finally, we run a least squares regression to examine correlates of FCC overstatements. The dependent variable is the overstatement ratio of coverage from any ISP in each census tract, where a tract is the smallest collection of census blocks for which the Census Bureau publishes demographic data. The independent variables are the proportion of the tract population that is a minority, the proportion of rural census blocks in the tract, the ISPs serving the tract, and the tract state. Here, we highlight that we find a significant negative correlation between both minority population and rural block populations and overstatement ratio, keeping in mind that a lower overstatement ratio implies greater overstatements. We present the full results of this analysis in our paper. Note that the R-squared value of our model is low, which means our model only explains a small portion of the variance of the data. In summary, we reverse engineer the broadband availability tools of 9 major ISPs, query them for millions of addresses across 9 states, and categorize the responses into a taxonomy of coverage outcomes, which we validate against real-world outcomes. With this coverage dataset, we contribute the most rigorous and largest scale evaluation of the SCC's broadband coverage maps to date. With conservative methods, we reveal significant overstatements of coverage across multiple dimensions, and we show how overstatements are particularly prominent in the rural and minority communities that lack coverage most. Our results demonstrate a promising direction for evaluating coverage maps in the US and abroad, and we urge governments and others to consider our findings when designing future broadband coverage maps. Thank you.